So in this video, we'll describe the first method to check whether certain infinite series is convergent or not. And let's look at this special case. We call an infinite series a geometric series if the ratio among the two consecutive terms for any pair of two consecutive terms, I would like to emphasize, is actually the same for all n. And it essentially means that, for example, if you look at this pair, for example, the ratio is A2 over A1. And if you look at the next pair, the ratio is actually A3 over A2, right? And I call this ratio the same if it happens that A2 divided by A1 is the same as A3 divided by A2, and the next pair is A4 and A3, and so on. In that case, we call it a fixed ratio for the geometric series. And if you notice that certain series is geometric, I claim that it is so easy to check whether it is convergent or not. But anyway, let's look at some simple examples first. So please look at the part A for this problem, whether an infinite series is geometric. I think this case is quite obvious. The answer is yes, because of the fact that if you look at the multiplicative ratio among the two terms, like you have to use 1 over 2 to multiply to the current term to get to the next term. And similarly, you can use the same number as the ratio to multiply to the term number 2 to the term 3. And similarly, every time you get to the next term, you are using the same multiplicative factor. In that case, we call it a geometric series because it essentially means the ratio among two consecutive terms is the same. And now the ratio is basically the same as this, which is half. So this case is a geometric series. Let's look at the next case. So please look at the current case now. You have to check whether the multiplicative factor that you use to get to the next term from the current term is actually a fixed number or not, right? And let's look at the first pair, which is the first number and the second number. And you can notice that you have to use minus 2 over 3 as a multiplication factor to multiply to this to get to the next term. And similarly, for the next pair, you have to use minus 2 over 3 as the same ratio again. And similarly, you have to use minus 2 over 3 to multiply to the number 3 to get to the fourth term. As you can see, we allow the ratio to be negative, right? Negative ratio essentially means you are changing the sign of the next number. Anyway, this case, we still call it geometric because we noticed that the ratio is actually fixed minus 2 over 3, at least from what I saw here. And let's look at the next one. So please look at the next one here. It is definitely not a geometric series because you can see the first pair actually has the ratio half, but starting from the next one, you are not getting the same ratio because for the next pair, you have to use the ratio term 2 over 3 to multiply to this number to get to the next term. And moreover, for the next ratio, it's gonna be 3 over 4, right? And you can see the ratio among any pair of consecutive terms is not fixed. And it gives you a sense that it is not a geometric series, right? So now, after noticing that some infinite series are actually geometric, there's a famous geometric series test to test whether certain infinite series is convergent or not. Let's go to the next part. So it is called a geometric series test. If an infinite series is geometric, I think we can actually write it by using only two parameters. Of course, the R, which is the fixed ratio, is so important. It governs how the numbers are changing along the series. And the first number is also important. I think by using these two parameters, you can actually write down all the terms you have in the geometric series. For example, the first term is basically A, right? And the next term, we can multiply it by the fixed ratio R to get to the next term, which means algebraically it's actually A times R. And the next term, once again, you use the ratio R to multiply to the current term to get AR squared, and so forth. So it means all the geometric series are actually determined by only two parameters, right? By using the two parameters, you can actually write down the whole thing for a geometric series. And now, I can claim that we have an easy criterion to test whether it is convergent or not. Let me write it down here. So please look at the criterions I put in the last two lines here. If the absolute value of the ratio is less than 1, then the series must be convergent. And I would like to add it up here. We actually have a very nice formula to understand which value does the series approach if it is a convergent geometric series. So let me put it here. This infinite series actually approach the number which is governed by a formula depending on A and R. The formula is A over 1 minus R. And this is the number that we expect that the infinite series, which is convergent, is actually approaching this fixed number. And of course, when the criterion is not satisfied, we know that the geometric series is not convergent and there's no point to use this formula, right? And let's look at a couple of examples here. Please look at the current problem. I'm asking you whether something is a convergent series depends on the numbers given to you, of course. And in the part A, we are seeing a series like this. And if you look at this kind of problems with the fixed pattern where the ratio is always half, we understand that it is actually a geometric series. Also, we understand that the first term, which is the first term up here, is actually half, and the ratio term is fixed, which is half. And by the previous page, where we just learned the geometric series test, we just need to look at the absolute value of the ratio, which is half now, which is less than 1. And that's why we understand that the geometric series is actually convergent. And even more than that, as I said, there's a formula that helps us find which value does the infinite series approach. It's actually approached by the formula is A over 1 minus R, and A is half and R is also half. So and which means that the infinite series actually approach 1 when you keep adding the terms here. We notice that the sum is actually approaching 1 gradually. It will never get above 1. And that's the answer to this problem. Right? And let's go to the next part. So please look at the pattern of the numbers that are changing along the infinite series. And if you just look at the first four numbers, let's check that it is actually a geometric series. Because, for example, the first ratio you need to use to multiply to the current term to get to the next term is actually minus 3 divided by 4. And same thing here, you can use minus 3 divided by 4 to multiply to the current term to get to the next term. And it's actually the same thing. Minus 3 over 4 can be used to get to the next term. And I think there's a typo here. So the fourth term is actually with the denominator 320. So anyway, in this case now we understand that it is geometric. And the first term is gonna be the first term up here. It is 4 over 5, and the ratio term is minus 3 over 4. And by the geometric series test, when you put the absolute value sign out of the ratio minus 3 over 4, we understand that we can take out the negative sign to get 3 over 4, which is less than 1. Whenever the ratio is less than 1, we understand that the series is convergent. And whenever the series is convergent, we can find the following. We can find that it actually approaches certain points based on the formula A over 1 minus R, which is 4 over 5 divided by 1 minus open bracket minus 3 over 4, right? And this number is actually the same as 16 over 35, and we expect that such a strange infinite series will approach this number. And let's look at the next case. So starting from now, we'll gradually use the mathematical notation, the sigma, which is called the summation, to understand the infinite series. And in this case, please try to understand what I'm talking about if you're not familiar with the sigma notation. The sigma notation basically means you're adding up the terms based on the term given inside here, starting from the counting argument n. N equals 1 is the starting point here, which means the first term. We can replace n by 1, right? Get the first term, and the next term is gonna be the same term, but n is replaced by 2. And the next term is gonna be the same term, but n is replaced by 3. And you can check this infinite series. If you don't fully understand what's happening, let's write it down. The next step is the same as 4 times 2 to the power 2 over 3 plus 4 times 2 to the power 4 divided by 3 square. The next term is 4 times 2 to the power 6 divided by 3 to the power 3, right? And I hope that you can see that for such a series, it is actually geometric because the first term, of course, we can just pick the first term, which is 4 times 2 squared divided by 3, which is actually 16 divided by 3. And for the ratio term, please check the fixed ratio. The fact is that 4 is like a constant. You are not multiplying 4 because every time if you multiply by 4, the power of 4 should go up, right? But now it is not going up. So 4 is like constant staying there. The power which is going up is actually the 3, you see. The 3 in the denominator has its power increased by 1 every time you go to the next term. It gives us a sense that the ratio in the bottom is actually 3. That's the factor you use to increase the power of 3 by 1 every time, right? And the next one is about the base 2. You see, every time when you look at the base 2, the power is increased by jumping from the current power by 2 to the next term here. And it gives us a sense that to make this pattern works, we need to multiply by 2 copies of 2 every time to get to the next term. And that's the reason why the power keeps increasing by 2, right? Or the other way to read it from here. This constant to the power n essentially means that you have to multiply by 3 to get to the next term. And this constant to the power 2n means that the pattern of the power is changed based on the 2n, which means you have to increase by 2 every time. So anyway, it essentially means that the power is actually 2 square for the ratio. And it is a geometric case, so we can use the geometric series test. So now the ratio term is actually 4 over 3, which is of course bigger than 1, right? So it basically means that the series is not convergent. And some people in that case use the word divergent to represent it. So it's up to you for the terminology. And when the geometric series is not convergent, of course, we don't need to use the summation formula A over 1 minus R to represent that. And that's basically the end of this problem. And we can look at the next problem here. Please look at the given infinite series. And once again, as I emphasize, if you're not feeling comfortable with the summation notation, you can actually write down the term one by one to get a better feeling of what I'm talking about here. As you can see in this infinite series, the first term is 2 over 4, the second term is 8 over 16, the next term is actually 26 over 64, and so on. I think it's quite easy to check that it is not geometric by itself. So we cannot use our test, which is the geometric series test. However, if you are being clever about the terms here, we can actually split the big term inside into 2 smaller terms. The first one is 3 to the power n divided by 4 to the power n. The next one is minus 1 over 4 to the power n, right? And in case you still don't know what's happening, let me write it down here. So please look at how it's like if you try to expand it term by term, and I hope you can try to take a look like this. You see this term? We can group all these terms together and put it in the first half. And then group the remaining term, which is having the minus sign all the time, to the second half. If you do this grouping, what you're getting is the following. You see, you're actually getting 2 infinite series, and for the first half, it is based on the terms, which is the first term in each bracket. And for the second half, it is based on the second term in each bracket, right? And now I claim that I believe that some of you can see it already, that both of these are actually geometric. Or the other way, I can write it this way. By the summation notation from the first line here on the page, we can actually split it into 2 different infinite series. Although the infinite series originally is not geometric, but the point is that after the split, we understand that both of these are geometric, right? And which means both of these can be understood by using the geometric series test. For the first one here, I hope you can see that the first term is actually with the n equals 1, which is 3 over 4. And you can also notice that the fixed ratio is actually 3 over 4. And this is the geometric series for the one. For the second one, we understand that the first term is actually 1 over 4 to the power 1, which is 1 over 4. The ratio term is actually the same as 1 over 4 again. And you can also look at it here. It's clear that the ratio is actually 1 over 4. Same as this group here, the ratio is 3 over 4. Anyway, essentially, you are having 2 geometric series. You are taking the difference of them. And I think for the first geometric series, it is actually convergent. The same happens to the second geometric series, right? It is also convergent for the second one. It means what? It means just for the first series, it actually approaches based on the formula, which is a over 1 minus r, which is 3 over 4 divided by 1 minus 3 over 4, based on the parameters here. And the answer to this is actually 3. And for the second series, it actually approaches a over 1 minus r again, but the ratio and the a is both 1 over a. So it is actually approaching 1 over 3. You see, basically you have a convergent geometric series minus another convergent geometric series. And we expect that it basically means the answer finally is the series is actually convergent. Although it is not geometric itself, but we make it look like the difference of two geometric series. At the end, we still can understand it. It actually approaches 3 minus 1 over 3. So it is the same as h over 3 at the end. That's the number we expect that the geometric series is approaching. That's the end of this video.